this is the first newbie bit where someone's going to be screaming because this is called pipelining because it looks like a CPU pipeline. So what we learned in computer architecture about CPU architecture is that one easy way to make purely sequential programs go faster is that if you have something that is busy in stage 1, but not leaving stage 2, you can already, sorry to say this in reverse, if you have something that's busy in stage 2, but stage 1 is not busy, you can already do some work in stage 1 while stage 2 is doing its thing. And similarly for S3, if S3 is doing something and those two compute units are not doing anything, then you can do something. So for CPUs, usually you have some stage that's called fetch, and then you have one that's called encode, and one that's exec, and memory, etc. writing. But the point is that while you're decoding the current instruction, you can already fetch the next instruction. So this supposes that you have a list of jobs to do, and then each job you can start doing the next one. And there's no eraser here, is there? Well, I guess my hand works. Kind of. Okay, and what it looks like is that while you're doing S2, you can have another thread work on S1, and when you're doing S3, you can have another thread work on S2, and a third one work on S1. So each one of those stages can be conceptualized as a thread, and each one of the layers as something that takes a result from the previous thread and give it to the next one. And then you have a basic notion of pipeline. Now, why is this called pipelining in dependent types? First, before we get to dependent types, we need to get to, is there really no eraser?
Send the run to the last, steals me.
The first thing we need to jump to is functional programming, because if you do some functional programming, you can conceptualize those stages as function and say the implementation from B to E can be seen as function composition from, well, in reverse, S3 composed with S2 composed with S1. And while this is great, it would be nice to be able to talk about the iterative steps before you talk about the implementation, to separate the specification from the implementation. And one of the use cases for me was I have a very linear job, which is to compile with a with a single pass compiler a file. And I might assume that I could have tons of files, but because my compiler is single file, single pass, I don't care about dependency between those files. I just want to deal with as many files as I can. So this is where we can start programming. We have here a basic layout for a compiler. So at first we have a stage called lexing, so that would be the leftmost stage. Then we parse a list of tokens into a tree. Then we do some type checking that gives you some semantic information. And then from the semantic information, you get some code. And you can write this program as saying this is codegen after type check, after parse, after lex. And that works. That's great, but now the problem is that, well, the thing I would like to elucidate is like, how can I talk about the intermediate stages that don't appear and get hidden in this hierarchy here? So the first thing to do is to think about, we're going to use the layers, and we could consider those as a list of types. So we're going to define a pipeline as a function from next to type. And it's simply going to be a vector of n types. And need to check. I already forgotten how I set up the slides, so yes. And then you can define the compiler pipeline as one of those. Pipeline as a pipeline of 4 stages. So 5 layers. Actually, just leave it out.
And this is going to be, the first stage is a string, the second stage is a list of tokens, the third stage is the tree, then semantic, and then bytecode. Okay, so we've not done it not quite yet, but what we want to do is to think about this as the specification and then have a program that runs this specification. And here we are going to define the program as those functions here. So if here the pipeline is Bij, then what we need is we need one function S1 from B to I, a function S2 from I to J, and then S3 from J to E. And there's a very easy way to do this. And the pipeline, well, here I should probably do pipeline, right? The implementation, what must have happened? Implementation of pipeline needs to be at least 2 because you need a place to start and a place to end. Otherwise, you don't have enough places to do everything. So in the base case,
Well, unless you don't go anywhere at all, of course.
Yes. If you don't go anywhere at all, you could have, I guess, one element. And here we're going to have the rest of the arguments. And you can choose whatever representation you want, but to be clear and simple, we're going to say in the inductive case, you get the first 2 elements, you make a function out of this, and then you take the rest, and you simply keep going until you are done. Oops. Okay. And now with this, what we can do is we can check what is the type of the compiler pipeline. So if you write compiler implementation, this will be the implementation of the compiler pipeline. I don't know why I did errors like this. Okay. And here we do get indeed a series of pairs that are each of them a function that takes one argument and brings it to the arguments of the next stage, which is exactly what we're looking for. And therefore, the first stage is lex, the second one is parse, the third one is forgot the type check, and then cogen. Okay. And currently, all this data is purely static. We've not done anything quite yet. This is where things start happening. So with a pipeline and a matching implementation, so this is what those 2 tidbits here, oops. It's what those arguments are. It's given a pipeline and an implementation for it. We obtain a function from the beginning of the pipeline to the end of the pipeline. And the way to implement this is, thankfully, exactly as you'd expect, because in the base case, you have at least x and y. Well, let's play A and B. You have a function f, and we don't need this argument. And here we have A, B, C, and we have another f, and the rest of the f's, and the rest of the function. No, like this. And so in the base case, given a pipeline that starts in A, that ends in B, and an implementation for it, which is, again, a function f to b, we can simply return f. And for the rest, we see that we start at A. We have a function f here that also starts at A. So we can pre-compose with f, and then we can ask what's going on afterwards. And we are given an implementation from B that goes all the way down to D. And we need a function that takes a B and returns something that goes all the way down to D as well. And this is the CD and FS. Okay.
And this is why I wasn't joking when I said you should consider being able to do nothing. Because you've got effing twice. So this is golf, of course, what I'm saying.
Right.
I mean, it's a good idea, but there's a little bit of repetition that you could golf work.
Yeah, I mean, there's more repetition that we're gonna go through first.
If you define impl as an inductor family rather than recursively, you don't need to match so much on the pipeline output.
Oh, okay, yeah.
That's it.
So actually, I'm not going to do that later, but I should probably do that in library.
Yeah.
Because of the 3 plus the definition of pipeline, you're going to go with them.
Mumble, 3 categories.
This is very 101.
Okay, so then we can recover what we saw before. So before we had a list of, well, a sequence of functional compositions. Now we can run the pipeline given a specification and an implementation. And what that gives us is a way to talk about the pipeline separately from its implementation. So you can start concatenating pipelines or concatenating implementations and see what happens. Okay, so we already skipped there, but this is not real. Compilers are not pure functions. A real compiler, this is not related, by the way, because there's no implementation, but a real compiler has some sort of effects, right? And those are the same functions, but I wrapped a maybe around to indicate that there is some effect going on. In this case, we might not actually succeed in compiling something. And this does not merely fit end-to-end as a pipeline. You need a notion of composition that's a little bit different. So this is the same function as before, but we're parameterized over a functor, m, and we're saying in the base case, instead of returning x to y, we return x to my. And in the implementation case, to run it, we require m to be a monad and replace the composition by kleisli composition. And what's neat about this is that it's essentially the same condition as this one. When I said there's more repetition coming, this is what I mean. And there is maybe a way to abstract over this. And this is going to come, but before we need to double check that our work does actually work. So given a monadic implementation of the compiler, can we run it? And that would mean that we do run compiler m from string to maybe bytecode. And this should be the same thing. This should be run m with the same pipeline, but a different implementation here. Why does that not work? I didn't give monad. Okay, and the implementation here is a list of functions that this time go to maybe. So this is lex m, parse m, check, and function. And we've done not much, but it works. So the basic premise here is that is achieved because what we can do now is keep the same pipeline, so keep the same semantic information about what stages we're interested in, but change its runtime characteristics, its runtime representation. So here we can run it into monad, or we can run it in a way that's pure, simply by changing the run. Another thing we can do that I've not shown here is that this can work for other things like debugging. So if you want to print every single stage because something wrong is happening and you want to find out what it is, given another implementation of run that would print each stage, you can see every stage appear. And that, again, gives you more flexibility in writing code without having to change much of your actual logic. Okay, I forgot. Yeah. So one of the reasons for this to be an interesting topic is that it allows you to get performance for free, essentially, if you have lots of things. which is very obvious. Well, not very obvious, but it's obvious if you do if you work with pipelining CPUs before. So if you have 3 stages, for example, and you have 3 jobs that each of them take 5 seconds, you can do them in parallel as fast as this diagram shows. So each one of those square is a job or a work unit, and the total length is the total length of time it takes to run the job. And what I've done here, we need to change multi-core. Here we go. So this is an example of a different pipeline, but with a multi-core runtime, where every stage is run in parallel given a sequence of inputs. So here is, here are 3 inputs. Those are names. Where are the inputs? Already, there we go. So this pipeline does something very simple. It takes a string, it will compute its length, it will double it, and then it will print it. And those functions are represented here. The pipeline starts with a string, we get its length, we double the length, and we print out the results. The trick is that we're making them very, very slow. So each of them takes 5 seconds to run. If you have 3 of them and you're running 3 stages, each of them takes 5 seconds. How long do you think it takes if you run them sequentially? This is the class paying attention test. So if you take this diagram and you have 3 of those, so you add 3 more here, and each one of them takes 5 seconds, then you have 15 seconds here, 15 seconds there, and 15 seconds there, so that's 45 seconds. But if you run it like this, where you start as soon as the first work unit is available, you have 15 seconds here, you add 5 seconds here, that's 20 seconds, and you add 5 more seconds here, that's 25 seconds. And well, the first one's already done, now we're waiting the remaining 45 seconds for the leading version to finish. And all the logging is simply saying, doing this dance of getting the first input, saying, I've got this input, I'm getting to the next stage, here's the next stage input, and the next stage will say, oh, I'm starting to work. And that's what got there we go. And so let's make this bigger. But indeed, the multi-core computation, even though the workload is purely linear, takes 25 seconds, whereas the single core takes 5 times 3 times 3, which is 45. Again, what's great about this is that we've not changed anything about the implementation. We've simply changed what runtime we're using. So here we're using the multi-core runtime, and it's faster. I need to go back to here. Yeah. This one? Yeah, okay. So this is where things become interesting. Well, they weren't interesting in terms of software engineering, but this is where they become interesting in terms of theory. The one thing we want to do is we would like to avoid this duplication of code, because if we look at those 2 functions, they are essentially the same. The one difference is the operator here at the end. So here we have a dot, and here we have kleisli composition. So we need some notion of abstracting over composition. We need a structure which base characteristic is the composition. and if you, well, we know that a category is the right tool for this job, and we can abstract over a category, saying that a category is given by a set of objects and a set of arrows. And I should have copy pasted this. But for the singleton case, we have an arrow from X to Y, and for the left over case, we have a pair of an arrow from X to Y, and the rest of the arrows, which is implementation from Y, Z, X, S. Okay. And now running it is a little bit different because now we're not executing program, but we are stitching together morphisms. It's not really the case that those morphisms turn out to be a function. They can be something else. This is why the return type of this is not a function. It's an arrow from the head of the pipeline to the tail of the pipeline. And its implementation will be the same as before. Actually, I can paste what I have up there, and I think it will work. If I take this, and I paste it here, run cat. There we go. So now we have one single definition that runs for any category, and will take any implementation and will run it. It is worth noting that we still haven't changed the pipeline. The pipeline, well, we have changed the nature of the pipeline. It's a list of objects now, not a list of vector, not a list of types. What now we can do is run the compiler.
I have a question.
Yes.
Can you scroll up like one page?
Like
Yeah.
You want to see this?
What is this syntax parameters?
Ah, sorry. Yeah.
Is that Eclipse or is that André Videla's?
No, that's citrus.
Never seen that.
It's it says add all those parameters to every function that's in this block.
The implementation is really body, so.
Yeah, don't rely on it. It only works in those cases. If you start having data definitions in there, it's nightmare. But we can use run cat, and now we can tell it. It was explicit or implicit. So run this category with as object types, as morphisms functions, and the compiler, the pipeline is the compiler pipeline, and the implementation is the compiler implementation, and that should just wait. There we go. And now if we do the same, and I'm going to keep myself for not having it already written down. So the objects are, yes, the objects are types. The morphisms are kleisli morphisms, and the compiler implementation is what I had before, so that's lex. I need to wrap them into kleisli, I think. Lex kleisli parse kleisli of I check and kleisli of gen. Kleisli, I need to tell kleisli prism maybe. There we go. All right, that's pretty cool. So given the same pipeline and the same run function, we can both work with pure functions or effectful functions. And what we have to change is this parameter saying what category are we working in exactly. And that's very powerful because now we can work not only with functions and effects, but with other things than functions. So I'm using this, for example, when I have big lists of containers, I can just say, here are the layers of each domain and codomain of each morphism, and then give the list of morphisms, and it will go. Okay. So this is where things get really wonky, and I would like to get feedback, because this is where the bit where I start not knowing what I'm doing, and I just find things that work without understanding why they work. Because we're working with dependent types, One of the great things that we can do with it is that we can talk about those types as first-class objects. So we can talk about those lists of objects or those lists of types. Concatenate, operate over them, take the head, take the tail. But we've not said how to cope with pipelines which intermediate results depend on previous results. So here's an example of a lambda calculus where we have multiple stages that depend on each other. The first, I'm going to write it down because otherwise it's going to be extremely confusing and hard to follow. So the main idea of this pipeline is that your first stage is a string. Your second stage is a list of token. This has not changed. Your third stage is an untyped lambda calculus. And, no, that's it. Your fourth stage is a list of variables. And a scoped lambda calculus over those variables. And your last stage is a list of types. List TI such that you have a well-typed representation, and we're going to match each type with each variable, and the lengths are going to have to be the same. So those are vectors, but I forgot. We're going to say this is just a zip of the variables and the types. Right, and this is, I hope you can agree that this is not too outrageous in structure. It feels like something you want to do if you're writing a compiler for a course. You do a single pass compiler, you want to collect all the variables, you want to check that they scoped, and then you want to check that they type check. And in the end, you have a very nice representation that you can start working with. But it's not something that can be represented easily with a pipeline because each element for each object of the pipeline is independent of the others. So instead, we're going to represent not pipelines as vectors of types, but as telescopes, saying this telescope starts with a string, and we don't care about what we're doing with it because nothing depends on it. We don't care about the tokens either. We don't care about the lambda calculus. We do. We do care about the scope representation because it contains the variables. The variables are reused here. And I don't think we care about this one. I think I missed something, but I don't remember what it is. So we're going to keep going. And the one thing that's going to be that's going to have to happen is that here we're going to have to extract the bars and say that this is actually sc.iy.
Well, you did have the bytecode, right, in the original time. Maybe what you said.
Yeah, but the bytecode does not depend on
It could be
it.
translated.
Oh, yeah, that's a good point.
So do I have it here depending on anything? So I have those functions here, right, okay. Yeah, I don't have it here depending, but this could further depend, right? Oops, go back here, okay. So each one of those layers, the first layer, lexing remains the same. Parsing is different because it returns a lambda calculus. Scope checking takes the lambda calculus and returns the number of variable it found, the variable it found, and the scoped lambda calculus. And type checking, given the list of variables and a scoped term, will return a typed lambda calculus with those variables attached to those types. And I should say, this is the type for the scope lambda calculus, so it's indexed over a list of names, and the type lambda calculus, it's indexed over context, which is a pair of names and types. Okay. Do I have it implemented directly? Okay, so I already done this. Thank goodness I wrote it because writing it by itself is complicated. So this is actually almost exactly what I have here. The difference is that sigma is written with this syntax where you give a name and then you say products and then the rest. And then you give another name, product, which is booked lambda calculus. So this is the scope representation saying in this stage we have a number of variables, a list of variables of that number, and a term of the lambda calculus. And in the next stage we have types and a lambda calculus that's indexed over this like first second thing is what this is here. And then we're done. So now the question is, we have to do the same thing as before, but it becomes quite tricky because we want to do two things. We want to handle the dependency, and we also want to handle the effect, because here all those things are surrounded by maybes, indicating that it can fail. And this is where I'm starting using something special, which is I'm going to erase this because it's already on the screen. Leave my marker. An implementation for a pipeline given by a telescope. Let's say T is a telescope. Its type cannot be something like head of T to tail to the last element of T. And the reason is that the last element of T will depend on all the intermediate steps that are in here. So a solution for this is to say that a pipeline that starts in T, or a pipeline given by telescope T, is a, and I'm going to pattern match here. I'm going to assume the telescope is not empty, so we have TS. It starts with a value of type T, and it's a pi type towards, it's called environment, oops, the signal, to the environment of TS of P, and the environment is the sigma type that is created by taking all the intermediate values of the telescope, such that if you have, I'm going to do it like this, end of panel to time. If we are empty, then our environment is unit. Sorry, let me this. And if we are not empty, TS, then this is the sigma type of V of T, followed by the environments given by this telescope at this value D. So TS of D. So the first parameter is the beginning of the morphism that we're going to build, and the rest is the environments of all those intermediate results. That's the final type we're looking for. Now we can't, there's something that's not shown here, is that we're also working inside maybe. So we actually, if we build a function that, for example, let's say, I'm trying to justify this magic trick right here. If you're given a function a to mb, but b depends on a, you can write it like this, right? Now, if you want to write a function that's f, if you want to write a function that depends on the result of f, like g, that takes an a, you cannot do n of f v. Because this is of type MV, but this functor expects a type here, not a monad. We need to somehow extract the V out of this monad to get a value that can be type checked by this function. So the trick that I'm using is that
C there. I mean, F of V was never going to be a type.
f of V was never going to be a.
Even if the M wasn't there, it'd still be a. I think you're on a C, which is depending
On Vn.
You mean like this?
yeah. But that still doesn't work.
Yeah. It's still yes, that's the correct thing to write. But the point is that it does not work.
Okay.
So what I'm doing is that because I'm working in this monad that I know about, I will write a binding function that will take a value v of type n of a, and then a continuation k of type v of a into n of, I guess this would be c of v. And I should not call those things the same name. R. There we go. And so here this a is the same, and this function is the dependent continuation of a bind operation of the monad. And therefore, with this structure, what I can do is, given a telescope, an arbitrary telescope, I can define the implementation of a pipeline as a telescope as a sequence of those binding operations. So the info of the telescope T is given by, if we're done, we're done. But if we have more things going on, TS, then what we need is we need to obtain a partial result, which is M of A, and we need a continuation for what is happening afterwards, which we're going to do with V of type, sorry, M of T, V of type T, to the rest of the telescope given at position T. So that's info of TS of V. Okay. So now this is why this next function here, to info, is this function info on the board, given the monad M. So here M is maybe, as a sequence of partial results and continuations that are sequenced like this. So at first, we actually, let's, I can do it interactively so that we can see what's going on. So what is the type here? Here's called decont pair because it's continuation pair of something, blah, 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 blah. But we know that we start with tokens. And the first partial result is the result of lexing the input file. And then we continue, and we can ask what's going on. And then again, we have a continuation pair where we expect a lambda calculus here. So we're going to say the tree obtained by lambda calculus is the results of parsing parse tree of the token. Yep, that works. And then we can keep going. So then the next stage is this monster here, which is the partial results of doing scope checking. And I think I'll just take this.
Yeah, you very much have to know what you're doing when you try and use the interactive editor.
Mm-hmm.
And it's quite difficult if you didn't know what you're going to do.
I mean, so what I found helpful is that this is essentially bind with dependency. And the problem here is that there's a lot of computation here. There's a lot of grades line going on that is hard to decipher. But if you look at the telescope, it tells you what's going on a little bit more clearly. And that's, to me, that's the more important bit, because that is the spec. And then the imputation, there's just the imputation. It doesn't have to be nice. Yeah, that works. And so we can use pattern matching in there to get the values that we extract instead of using projections, etc. And then, okay, this is difficult, but
Right, so it's funny because in your pipeline description, you said we didn't care about the tokens and so on, but they actually show up in the.
yes, this is what I'm going to show here, is that in the end, we still want this function, right, from start to end. And we want the bytecode. Well, the bytecode does not depend on anything, so we still want this function from A to B, but we have a lot of intermediate steps. So I'm running the dependent pipeline. I'm obtaining all the intermediate results from each of those types. Actually, let me see if I can get arg. Yeah, they're all separated. Let's just do this. So that result is this. Right. So if you simply run the dependent pipeline with the telescope and with the appropriate implementation, you have a huge sigma type that does not contain exactly what you want. So to obtain this need function, you need to do a little bit of pattern matching, extracting what you need. And the easiest, well, the most readable way to do it is to map the nicer and extract the last before last step, the one before the last step, which is the bytes, and then you return the bytes. Okay, I only have 10% battery and 10 more minutes, so I'm done. Well, I'm done. There's one more thing to say about this, which is we can further generalize the previous pipeline, which is merely categories, to use graded categories. That is to say, we are going to parameterize over a monoid of grades, an arrow of, well, a set of graded arrows, which take a grade, two objects, and then that gives you a morphism. And given a way to fold grades using the monoid operation, we can build a graded pipeline that will work if you give it a set of layers, a set of grades for each result of the layer. So there's, because, where's yeah. So the variable bars are the layers, because each function or each morphism here goes from one layer to the other, there's always one morphism less than the amount of layers. And because each grade is attached to the morphism, there's one less morphism than the amount of grades. We can define the same thing as before, except using graded morphisms. And for the implementation, we do the same thing, except we use graded morphism position. And then I didn't have to finish this, but I promise it works. Actually, do I have an example? No, I don't think I have an example. If you have, I'll just write down because it's easy. So one of the things we started doing in production, I swear, is that if you have A to, well, GRB and B to GR1, GR2, C, composition of those things gives you, and I'm going to say the monoid is plus here, gives you A to GR1 plus GR2 to C, right? One of the monoids that's really nice to use for grade is the free monoid types, because if you represent errors using the free monoid types, then to indicate that you have no errors, you give an empty list. If you indicate that you have one error, you return a signal to this. Or if you have two errors, two kinds of errors, you return the list of two elements, and that is, let's say, C to D. And then the position of this pipeline will result in what do I do? Yeah, A to GR1 plus GR2 plus GR3 to D. And things that don't return errors are not counted, which looks fine. Realize that things that have repetition are counted twice, but that's future work.
If it's production code, the pipeline at the end probably has error type string plus string plus string plus string.
What returns do they have?
Well, currently strings, but
It's work in progress.
Yeah.
I don't remember. I did try on my own, and I had essentially each stage had different error, like scoping error, type check error,
Yeah.
lexing error, right? And so this repetition did not show up in that case. But like, for example, the first stage is just splitting I have one more stage that's trivial, which is split the string into a list of lines, and that never returns errors, and so that's always the empty list in terms of the grade of errors. Yeah, and then you need in the end to turn this into a type, so this will be turned into the type A to it's called one out here, but it's the sure you understand. One out A G1, G2, G3 isn't either one of those or D. And that's the resulting pipeline by grading each morphism with what errors they can have. And this should also work with containers. I have a type check, I just don't have a good example for it, where the grade is given by the power construction of containers. That's it.